Okay, so we've got a massive problem here about RLC circuits. This problem, as you can see, is multiple part, and overall it really kind of touches the entire breadth of the complexity of these RLC type problems as far as we'll get. We see that we have this uh, voltage supply here, which is an AC source, and we've got a capacitor, 40 microfarads, a little curly inductor, and a 15 ohm resistor. And that's the makings of your R, L, and C in your RLC circuit. So let's read the problem a bit. The following circuit is used to send a signal using a 15 ohm resistor. There is a 100 millihenry inductor and a 40 microfarad capacitor attached with the resistor to a 60 volt AC source with a variable frequency. Okay, when we read something like that, we got to make sure we're sort of in our head highlighting the keys here. As the following circuit used to send a signal, that might be important, but maybe not. Using a 15 ohm resistor, okay, that sounds like an ohm value, R, the resistance. And this is a 100 millihenry inductor, that's our L, and a 40 microfarad capacitor, that is our C value, attached with a 60 volt AC source. Variable frequency. Be very careful. That 60 volts, this is an AC circuit, and so by default, 60 volts AC is not just V, but it's actually equal to VRMS. VRMS is 60 volts. Okay? Now part A says to sketch a plot of the IRMS current as a function of the driving frequency, F. Make sure your axes show important and correct values of F and IRMS. Part B, I've actually done a little bit of rewriting to make it more clear what I'm looking for. What is the average power drawn by the resistor at the resonant frequency? And C, a new signal is to be sent which has a frequency 10% lower than before. If we fail to match that frequency and instead keep our circuit the same, how much power will be used in that case? So, especially with problem A, you kind of just have to know the answer. This is an LRC circuit, and so this is all about resonance. And so this kind of a slide should be sticking out in your head, slide 12 from notes 11, that if we have an LRC circuit, it's going to have a peak. This F naught is going to be a resonant frequency, which you can find with the equation F naught equals 1 over 2 pi root LC. And that comes about by setting this guy XL equal to XC, because that's resonance. When the two reactance values of the inductor and the capacitor are equal, then this becomes 0. This becomes 0, and Z will be equal to the square root of R squared, or just R, the resistor value. F naught, this equation that I wrote here, is the condition that you need in order for these to be equal. And when that happens, we have this nice peak at the top of the LRC circuit graph where we've plotted the IRMS current over different frequencies. And that's our little sweet spot there. So that's kind of enough to get started with sketching the plot. Well, you just sketch exactly something like from what we just saw. Here's F, here's IRMS specifically, RMS, and it just needs to have a peaky value, and it goes down to 0. At low frequencies, and at high frequencies, low and high frequencies, the capacitor and inductor kind of kill the circuit, and they become like big, strong resistors. But there's this sweet spot in the middle. Oh, not exactly the middle, just somewhere in between. And this is what we call F naught. So this second part of the question asks me to make sure my axes somehow show the important and correct values. That means that I want to see not just that I've written F naught and maybe IRMS max or something, but I want to see the actual number that goes into here. And so what I'm saying is compute F naught, but we have an equation for that. That's 1 over 2 pi root LC. L is equal to the inductance of the inductor, which is 100 millihenries, which you can put into SI as 0.100 henries. And C is equal to the capacitance of the capacitor, which is 40 microfarads, or 40 times 10 to the minus 6 farads. If you combine these and put them into this equation, the 1 over 2 pi root LC, then you'll find F naught equals 79.58 hertz. 79.58 hertz. And this is going to be important. We're going to need this value, so we're going to keep it for now. And that's where F naught is supposed to be. What about this peak here? What's the value of the current there? That's another value which we can find out because at that point, at F naught, right, Z is going to be equal to square root of R squared plus 0, because XL and XC are going to cancel each other out. And so it's going to be equal to R squared, and then you take the square root. So Z just equals R. And we can use that information to find IRMS, okay? So keep in mind, we are still following the loop law and Kirchhoff's, the junction law, actually more relevant in this case, that if at any point in time the current will split off at junctions, and conversely, if there's no junction, it's not going to change. So whatever the current is of this system, it's going to be the same throughout the entire circuit. And so what happens is we need to find a way to find, well, we have the 60 volts, but I need some sort of a quantity to help me find this current across this entire system. We cannot just use V equals IR as the, and use that to find the current. We can't just do that because of the loop law. Essentially, we have this 60 volts. We don't know if this is going up 60 volts. We don't know how much is going down across each element. It might be 20 volts and 20 volts and 20 volts. It might be, but it could be more complicated. Maybe it's minus 50, minus 5, and then minus 0 across the resistor. So you can't use V equals IR. You cannot ignore the capacitor and the inductor. And instead, the way you find the current is with V equals IZ, right? Very similar. It's like a Ohm's law type equation, except essentially what we're doing is we're treating all these things as one, and in that case, then we can treat them all as being under 60 volts. And so we can plug in 60 volts for V and plug in the Z value, which luckily for us, since we're at resonance, we can put in just 15. And so since V equals IZ, and keep in mind these are always RMS values unless otherwise stated, then I equals V over Z, then this is 60 volts over Z, which in this resonant case happens to be 15 ohms. And so this gives us 4 amps as our IRMS, as the essentially the maximum value right there. And this is going to be useful as well in the problems moving forwards. So 4 amps is our maximum current RMS, and F naught is about 80 hertz here. Okay, part B says, what is the average power drawn by the resistor at that resonant frequency? So this is where we're going to make use of the loop law and the junction law. We've already computed the current at F naught, right? So this goes around, and we know that this resistor is going to feel I of 4 amps, IRMS of 4 amps. And we can see that we know its resistance value, R, is 15 ohms. That's enough. That's enough to answer the question because the power is going to be equal to power average equal to I RMS times V RMS. But since V equals IR, this is going to be just IRMS times IR, or IRMS times R. And so this is going to be the power is pretty much used by the resistor. So this is just I squared times R. So this is 4 amps times 4 amps times 15. So let's see, 16 amps squared times 15 ohms. And this is going to be 240 watts is the power stolen by the resistor. And that's it. That's all we need for part B, actually. It's a very lucky case. Since we're at resonance, we get to get away with a lot of stuff. But this changes a lot, and our work becomes much more complicated in part C, where we have changed the resonant frequency. Or sorry, not changed the resonant frequency, changed our frequency, and we're no longer at resonance. So we still have the same graph where across the different frequencies we have this peak, and this is I RMS is the value here, and this is the maximum IRMS, except we're going to move a little bit to the left, and so we're not going to be optimal. We're going to be having some it's going to be lower than 4 amps, our IRMS current. And so we're going to ask, so we've gone down by 10%, and then we need to find the power in this case. So it's going to be the same idea, right? Like I need the current here, which is not going to be 4 amps, but if we find it, then we can still do P is equal to I squared R, okay, to find the power drawn by the resistor. And so we just need to find the I value now. And again, we can't find it just using the resistor. We have to consider that this whole RLC circuit behaves as one unit, and altogether has some sort of like a resistance-like value, which we call the impedance. Z is square root of R squared plus XL minus XC all squared, and they take the square root. And so this time, XL and XC will not cancel and equal 0, okay, since we're not at frequency anymore, at resonant frequency. XL is going to be equal to 2 pi times F times L. And our frequency is 10% lower, so let's do that real quick. We started at 79 almost 80 hertz, okay, 79.58. 79.58 hertz was our F naught, but we said we went 10% lower. That means multiply this value times 90% or 0.9. And so this is like our old resonant frequency. Our new frequency, which is not resonant anymore, is going to be, let's see what I got over here, 71.622 hertz. 622 hertz. Okay, and that's, oops, not a great 6, but that's what I got for the F value. Not the resonant frequency, but the frequency that we chose for this thing. And so we could put that into here in our XL equation, and we can still keep 100 millihenries. So this is going to be going into here. And for L, we are going to use the 0.1 henries, or 100 millihenries, same thing. And put that all together, you should have an XL value of 45 ohms. Okay. XC, same type of story. We've already computed the F value. We don't need to recompute it, but it's going to be 1 over 2 pi FC. So F is still going to be 71.6 hertz, and the capacitance is 40 microfarads. So you put into here 40 times 10 to the minus 6 farads, and what you should get if you do that is you'll get 55.55 ohms. So if we were at resonant frequencies, these two XL and XC would be equal to each other, and therefore when we subtract them in here, they would get 0, but they're not. And so actually you subtract them, you get something like 10, and so Z is going to be equal to the square root of still 15 ohms, this is our old resistance, squared, plus, something that's roughly 10 ohms squared, which is 55 minus 45. Well, 45 minus 55, it doesn't matter whether this is positive or negative. Actually, it does not matter which one you subtract because the square will get rid of that negative anyways. But if you do this, square the 10, square the 15, add them and take a square root, I think that you get something like 18.34 ohms as our Z value. Not quite 15, just a little bit above 15. And so let's take this forward. Let's clear our page. But first, let's remind ourselves of what our goal is. Our goal is to find the power at this resistor. And to do that, we need to know what the current is. And so we're going to use Z to find the current. So Z is 18.34 ohms. And our current, right? So we're going to have to follow this Ohm's law like thing, V equals IZ, but we're not going to have this nice case where Z equals R anymore. So we still use the 60 volts as that is the voltage across the entire circuit, but instead of 15, over 18.34 ohms. And so our final IRMS value here is going to be 3.27 amps, and you see that is smaller than 4 amps. Doesn't sound like a lot smaller, but it is significantly smaller. 3 amps is already a big current, 3 and 4 amps. And so final step is to find that power average, which, if to be clear here, is IRMS times VRMS. And we're asked specifically about the power drawn by the resistor. So this is just I squared R, or 3.27 amps squared, times the 15 ohms, not the 18. It's going to be the 15 since we're asked about the power drawn by the resistor. And this is 160 watts. If you do the math, you'll find that even though we dropped our resonant frequency by 10%, our power dropped by more than 10%. And that's due to this peaky graph. Like the further away you get, the more intense this effect of diminishing the power which comes along with the current is. So yeah, this is a very long problem. I think you can identify that it was much easier when we're at resonance. When we get off of resonance, it can make us have it to do a lot more math. But we just want to rely on the loop law and on the junction law to make our problems and our lives easier here. I think a lot of the problems or the issues in trying to solve this problem would be identifying exactly when I should be using R and when should you be using Z, R or Z. So I think the key is to remember that in this circuit with all these little elements, you might have a resistor here, what do we have, inductor there, and a capacitor. We've got to follow Ohm's laws, or sorry, the loop law and the junction law, that the current has to be the same. But think about the voltage as well, that the voltage drops. And so if you find yourself saying that, look, the voltage across the resistor is 60 volts, that won't make sense. It doesn't make sense because there has to be a voltage drop across the other elements. I mean, theoretically, it doesn't have to be for any given point in time, but just thinking about the loop law, it can have dropped by different amounts of voltage, and so you can't just automatically know the voltage across the resistor. All right, so this is a tough one. Do bring me any questions if you've got them, and hopefully that was helpful in answering this first problem. I had to rewrite parts B and C just a little bit to make it a little more clear exactly what I was asking about in terms of which power are we interested in. So yeah, hopefully this one didn't give you any trouble in the future. See you in the next one.